Hello, this is Dr. Tesler for Operating Systems COSC 439 and 519. This is the lecture that corresponds to day 1 of week 2, and we will be talking about operating system structures. What we should remember from the previous lecture are the following bullet points. What the definition of an operating system was, though it wasn't as concise or as consistent as we would like. What the responsibilities of an operating system are, what their goals may be, what a kernel is, what caching is, the difference between single, multiprocessor, single, and multi-core processors, what a process is versus a program, what memory and storage management are, and what protection and security are. We covered the roles of an operating system as a resource allocator and as a control program. And one of the views of operating systems that we wanted to maintain after the last lecture is this computer architecture which the operating system sits upon, where we have a CPU, a processor, or processors that are in control of the other controllers that are running code themselves, so a disk controller, a printer controller, a GPU, and how they share memory through a memory controller as well. So again, that system bus set, that's what we said was short for omnibus, for all, meaning that everyone can communicate across that bus, and that bus has a specific width, saying who can talk, when they can talk, and there may be some conflicts there. In a nutshell, our operating system manages our shared resources. One of those shared resources is the processor that allows us to have concurrency memory. That's how much available memory there is to a program, or to a process rather than a program. Controlling access to input and output devices, allocation, creation, and modification of files, communication over networks, and providing some kind of security for the processes and devices. One of the things that we want to keep track of, in particular for memory management, is if a process needs more memory than is available, how might the operating system facilitate that? Those were the summary points from the previous class. In this lecture, our objectives are to describe the services an operating system will provide, the ways that an operating system is structured, and a short description of how they boot. We will also talk about system calls, and in particular, throughout this lecture, what we want to focus on is the design, the structural components of an operating system, not necessarily at the lowest detail, but to understand why we might make bigger decisions and what details about hardware architectures or programming methodologies would lead to those design decisions. So the chapter is organized by the system services, the operating system interface, system calls, the different types of system calls, what a system program is, which we've covered a little bit, but we'll go a little bit more into it here. Then the design, implementation, structure debugging, and generation. We won't spend as much time focusing on debugging of an operating system here. That's in the book. But we will talk about it just a little bit briefly. So the services that an operating system provide, they vary from your definition. From a lower level definition, that might just be the interface from the program to the scheduler, to files, down to hardware access. Some operating systems may include a user interface. The most common elements, the most common operating system that includes a user interface, a GUI, would be Android or iOS, those mobile touch devices. With OS X, you don't necessarily need a GUI. You have the command line that you can operate with the system entirely from there if you wish. Linux is also familiar to those, but in both OS X and Linux, the user interface, the CLIs, and the GUIs are not part of the operating system exactly. They're user applications. You can have a shell in Linux that's bash, KSH, or ZSH, and because OS X is running FreeBSD, all those shells are available as well. Similarly, on Linux, you might have a different display manager, a different window manager. On Ubuntu, that's Unity, I believe. You might use XFCE or the Awesome Window Manager. There are other choices that you have. So the GUI doesn't necessarily come with an operating system, but the operating system may provide one like Windows does, and OS X as well. But what is common among operating systems is the control of program execution. where a program that is requested to be run by the user or the startup process is loaded into memory and begins execution. If an error occurs, like say divide by zero, that raises a trap, the operating system will handle that error and report it in some way, shape, or form. Additionally, the operating system provides input and output operations, saying writing to disk, reading from a GPU, or receiving a transmission over a network card. Further operating system services are file manipulation. Since we need files, that's the abstract concept that we use for persistent storage. And management of file systems is a large and involved topic. You could think of an object store as a file system, but an object store is not the same indexing mechanism as your directory structure that you're accustomed to on your PC. And on Android and iOS, the file system is even more vague, where files are accessed by their type commonly rather than through the directory structure. Again, communications that, depending on your operating system, falls in the same class of I/O operations. That just sending a packet over the wire might be something that you interact with the networking device, or in a higher abstraction that you need to send a TCP packet to someone would be communication, and that might be provided by the operating system. Another service is error detection, that there are possible errors either in program construction, that it, again, may raise a divide by zero or try to reach memory that is not accessible. Another type of error would be a protection violation, that a process tries to access a device it does not have permissions to access, or a file, pardon me, or some other restriction. The operating system should do its best to take action in response to those requests. An invalid request based on permissions should be denied, and the behavior of the program after that point can vary. That there may not be as defined a behavior when requesting access to a file that you don't have permissions to. The other portions of error detection may include some forensic pieces, such as a core dump, so that the user can debug what happened with their application. Particular services that, in particular, resource allocation is a service of an operating system that we rely upon. There are, on a modern machine, there are many processes running, there are many processors or resources available to be used, and their efficient allocation is a challenging task. We talked a little bit about input and output overlap while processing another task. There are other areas where efficiency can be very hard to define and achieve. We also want to account for those resource usage. So we want to see how much, in particular on a shared system, you might limit how much processing time one user may be able to use, how much of a file system they might be able to use, how much memory they might be able to use, and then protection and security. So the protection is a mechanism to ensure that resources are accessed according to permissions, and security is enforcing those protections. So the way that we look at an operating system is typically on layers, where we have the hardware at the bottom, the operating system just above that, then the services it provides, and those services are accessible via system calls, and that makes up the user interface to the operating system, is those system calls, that system call layer. And that system call layer may be a programmatic API, like the write call in Linux. We'll go through some others a little bit later. But those user interfaces are from the program's perspective. How do I access the operating system programmatically? A GUI might sit on top of that user interface to present information to the user, say in Microsoft Excel, or in batch processing, if a list of jobs are submitted to an operating system that works in a batch mode, or at the command line, where you might type ls in your bash command line to invoke the list of directory command, which would need to access a file through a system call, and then display that information through another system call, writing to the terminal. The command line interpreter is one interface to a system, and they are sometimes implemented in the kernel, sometimes by what the book is calling a systems program, and other times just by a regular application. There are multiple flavors. This one in our example here, I believe, is bash given the prompt. There's KSH, ZSH, and TCSH, several others, CSH, that you can choose from. And its purpose is to wait for commands to be issued by the user, execute those commands, and present the results. The essential operation of a command issued to a CLI is to perform the task and return the result. Returning the result typically is 0 for success, non-zero for failure, and that's all that there is. Now that might be a little confusing because you say, well, I said ls. That's a request to list the directory. I want to see the contents. Well, from the CLI's perspective, the side effect of the ls command is to display information. ls will display that information and then return a value to the shell. That is the shell's perspective, the CLI's perspective. Sorry, CLI and shell I will say interchangeably, I apologize. From the CLI's perspective, the request was execute this command ls with the arguments that are provided. When that's done, ls will return a value to me, and I will present that to the user. The side effect of running ls is to display text in the window. Similarly, ping, in the example on the slide here, pings a device, and the side effect is that it displays the round-trip times and the time to live information on the terminal. But the return value is success as indicated by the lack of an error message here. Shells can be built as standalones where they have all the commands built into them, or they execute additional programs. Typically, the latter is more common. GUIs are familiar, I think, because everybody has a cell phone. For a PC, though, the GUI is a little bit different. It's typically a desktop metaphor, which is a little weird nowadays, that it doesn't really look like a desktop where I might put a stack of papers or put a folder and then stuff papers within it. We have additional concepts on top of those. And for our desktop interface, we use icons to represent our files, our interactions, though I feel like this should be fairly familiar for you guys. What is important that it was invented at Xerox and duplicated all over. Typically, a computing system, a whole computer like the one you're sitting in front of, will have both a CLI and a GUI. There's PowerShell, just the command terminal on Windows as well, and on OS X there are several fully featured terminals such as RxVT and GNOME Terminal and others. Then you have the other flavors that come with GUI interfaces with the desktop environments like GNOME KDE or XFCE. This may not be familiar for those of you because not everybody uses OS X, but the general idea of Windows where applications reside is generally where we've fallen on for GUI interfaces. Touchscreen interfaces are more single-purpose typically, that we would have a set of icons. When we tap on them, they take up the whole screen, and we might be able to switch between them. We have notifications that drop down, but again, you're likely familiar with this because you probably use your cell phone. What's happening underneath when these GUIs or CLIs interact with the system is that they have to make a system call. And this is our abstraction, that layer between the operating system and the system programs or user-level applications. And they're typically available in a high-level language like C or C++, and that API is standardized for programs to use to interact with the system. You may have had some interaction with the POSIX API or the Windows 32 API. Interestingly, we have, for the Java virtual machine, there is a Java API as well, even though that is a virtual machine, which we'll talk about a little bit later. Somewhat confusingly, in the slides is at times they will mix between using the system call names from a particular API, whether that be the Windows 32 API, the POSIX API, and a generic name. This will require you as the reader or viewer to take a moment and say, okay, what is this name? What does it accomplish? What is it trying to do? If it's a simple name like get permissions, well, maybe that means to get the permissions of that particular object, whether that be a file or a piece of memory. So be careful when going through the slides that those names may not be actual system call names. So taking another perspective on system calls, you'll have to take a look at the slides for the link. That's a sort of important link as well. That you have a user program, and in this case, it wants to write somewhere. There is a C library that provides a wrapper around that system call that we just call write that moves the program execution from user space into kernel space to perform the write. What is missing in the book is a good example of how a system call is implemented, and it is hardware specific. The link that I sent you to there gives an example of how to invoke a system call using an interrupt. And keep that, you might want to go visit that link now. Keep that in mind as we go forward when we talk about implementing a system call. So a system call is typically a number. And that number, let's say that it's write. I'm not sure if this is the right number. We'll say that the number for write is 1. That I would need to use, pardon me. I would need to provide the system call number of 1 to the system call interface to then invoke that write method. The operating system is alerted that there's a system call on behalf of a program that needs to execute. The operating system then responds to that call, returns the value to the program, and it can handle any error cases or success correctly. Now, from the programmer's perspective, if I'm issuing a write call to say write to a file, I don't know anything about this, and I don't need to. The operating system has provided that API. I'm able to interact with it, in this case with libc, and none of those details are necessary for my understanding to use the write system call. But the ability to provide an interrupt, either in software or in hardware, from one process to the processor, influences how I design this system call. All of that, again, is abstracted away by the concept of the API. And when abstracting away those details, that allows you to write an operating system for that operates with, say, a write call on different sets of hardware with different sets of functionality. So in concept, we're in user mode, and we request an open. That system call interface causes the operating system to wake up in kernel mode, realizes, oh, hey, I've got the code for open and some arguments to open, say, a file. I will go perform that operation and then return success or failure through the system call interface back to that user application. So the return value is given to user mode where the application can, pardon me, can handle the response of success, error, or failure. There's an example in the book where they copy from one file to another. There are several system calls involved in that operation. If you when reading the book, if you are able to understand the sequence of events that occur, you will understand not necessarily the mechanism, but the concept that is a system call, that I would need to provide an input file name, ask the operating system to open it for the source as well as the destination, and those are two separate calls. When reading information and writing information, that those are separate calls as well. If you can understand that process, then you understand the purpose of a system call. So please make sure that you go through that example and have at least the rough idea of what a system call is. Each of these system calls is provided in a standard API, otherwise programs wouldn't be able to use them. And one example is read. Now, for the purpose of the program, read simply takes a certain amount of information out of a file and puts it in a local memory buffer because, again, processes only have access to information in their available memory. How this is implemented doesn't matter, not to the program user, but you as the operating system designer will need to consider how to implement such an interface. Clearly, when it comes to read, there needs to be a parameter that is, I need to understand which file to read from, or I need to know where to write to. And each of those calls will have a different set of parameters. There are different methods for passing parameters to the operating system. The simplest is to place some information in a register, and if all the parameters fit in the register, we need to do nothing more, just place those parameters in the register, invoke the system call. If there are more parameters than there are registers available, then take those parameters and put them in a special block of memory or in a predefined location, and then invoke the system call, where the system call will know where to look in memory to retrieve that information. We may also push information onto the stack, so the operating system may pop it, and the choice of each method is up to the system designer on how they want to implement a system call. Clearly, the most efficient is to just place information in a register. That's not a problem. Similarly, having dedicated memory for a system call is quick, not as quick as a register, but it requires additional memory, and that memory be reserved. Placing information on the stack is more complicated from a implementation side of the API and the operating system. But these techniques are all valid because they service the function. The read call that we looked at in this particular slide doesn't describe which of those methods to use because that's abstracted away on behalf of the user, on behalf of the programmer. And the example that we have on this slide is that of passing parameters by a table. The way that this works in this example is to have the table in a dynamic memory location. The table holds the parameters for the system call. That's the gray area on the right-hand side. In preparation for making the system call, the address of the beginning of that table is loaded into a specific register, and then the system call is made, in this case number 13. We don't know what that does. When the code for system call 13 begins to execute, it now has the address of the beginning of that table where it can consume those parameters. There are many types of system calls. In process control, we'll need to create and stop processes, ending or abort a process. So to end would be success, abort would be a request by another process to terminate another. To load a process into memory, begin executing it. If we want to get process attributes, that might include the owner, how long it's been running, its program counter, and who else might have access to it, also setting those attributes. We might want to wait for a particular amount of time. So a process may just want to go to sleep for a second, saying, I don't need to do anything for the next second. That's when I'll wake up. A process may want to wait for a particular event to occur or to signal an event to occur. This can be the response to another process releasing a semaphore or receiving a message. Processes allocate and free memory quite often in modern systems. There might also be the need to dump my own memory as a process because I know that I'm failing. And there might be debugging system calls after we've hooked into the particular loading of an application to inspect and examine its state. There are also locks that might be used to manage access to shared resources and shared data between processes, which we'll go into when we talk about methods of IPC. Additionally, there are system calls related to file management to create, read, and modify files. Device management, such as getting control over the GPU or audio device, and reading and writing to those devices, seeing whether or not they are attached in the case of, say, a USB stick. We might want to get some status about the system, like this current date, how long it's been up, or see how many processes are running. And communication is a large set of system calls. And there are different modes of communication based on the system. We might have message passing, we might have shared memory. So we need all of those system calls to properly communicate between processes and possibly communicate across devices. And as a simple thought experiment, when you try to make a connection to a website, you're not connecting to a computer. You're connecting to another process. So your computer, though it is connecting to another computer, when the web server is running, that's just a process running on that foreign machine. And when you initiate a connection, when you say, I would like your top-level web page, that process is making a request, a communication request. The server then receives that request. How do you initiate that request? Well, you make a system call to initiate communication. And how does the web server receive that request? Well, it's been waiting for an event that is incoming communication to wake it up. So that process was sitting there waiting for a communication event, and the operating system delivered it to it. So while it is true that you are connecting between computers and computers, it is more accurate to say that your processes are communicating. And you can use these same communication mechanisms to communicate between processes locally. And when an operating system is well designed, those two types of communication mechanisms are transparent to the users. And like all operating systems and programs, protection and security is the final thought. So again, we will have system calls to control access to resources, to get and set our positions, or deny access, or set permissions so that people may access, or revoke permissions so people cannot access particular resources. So these examples, the ones on the right are the ones I'm more familiar with than the ones for Windows, because I do most of my programming in a POSIX environment, which include most of these system calls as well. So we need to create a process, that's to fork a process. To exit your process, you're familiar with that, with exiting. Waiting for a process as well. We open files, we read files, we write files. In Windows, we create files, we read files, we write files, and we close handles. Interesting amount of parity there. So these are examples of functions that you may have used in your programs already and not realize that they were system calls. And at a further abstraction, the standard library of C provides the function printf. Well, the standard C library doesn't use the primitive, the operating system call of write at the user level, though you can. So write is the system call, printf is the library call. So when you printf, say in this case greetings, that will in turn invoke write, which operates at the system call level, invoking the operating system to then perform the write and return the value to the write system call, which is a function that returns its value to printf, which then returns its value to your call. So this is just to illustrate, yet again, what a system call is, transferring from user mode to kernel mode, where it has access to, say, writing to the display, because that would be a kernel mode only operation. The history of our types of architectures is based upon sort of just what worked at the time. And MS-DOS is certainly an operating system that just worked at the time. Its focus was on being minimal and being out of the way. So it was a single tasking environment, meaning you could run only one program at once. When it was booted, it would drop you right into the shell, which is part of the operating system itself. And this prevented the need for any kind of process control, because once you executed a program, the command interpreter would remove some of its functionality, freeing up more memory, so the process, which you see on the right side, could begin running with as much memory as possible. So this idea was that, okay, the computing resources are scant, they're scarce. DOS is only there to get a program loaded and then shrink down to as small as possible and let the program run as a process. This presented some problems that, well, every process would need to have all the libraries necessary to access all of the hardware underlying it, typically. And so that's one of the failings of DOS, but it was more popular than the developers expected, and it's stuck around for a very long time. You can still run it in an emulator or a virtual machine if you like. FreeBSD is a Unix variant that allows for concurrent processing. We should say multitasking, not concurrent. And the idea under FreeBSD is that memory is partitioned into processes, and when you log in, you get your first shell, that is your first process that a user can interact with, and from there, your shell allows you to fork more applications via the fork system call, and they are executed. Then the shell waits for those applications to terminate and resumes control. So again, we talked about this, I mentioned this earlier, that typically in these systems, 0 indicates no error, and a code other than 0 indicates some type of error. And the motivation there in the past was that success would have a standard value of 0, and then other types of errors, say out of memory, divide by 0, segfault, meaning you access memory that wasn't, you were not permitted to within your process, would be given their own individual error codes, just like you have a 404 for website not found, or 408, I believe, for access denied in HTTP requests. But through this, the kernel always sits in the same amount of memory on FreeBSD, and processes can consume and release memory as they need it. System programs, though, just like operating systems, are they lack a solid definition across operating systems. So they allow you to manipulate files, check the status of the system, modify files. Some support for programming languages sometimes exists there, like the C headers for the kernel that provide those system call APIs. Is that part of the system program? Not exactly clear. But one that does seem to be clear for all operating systems is to load and execute programs, provide communication mechanisms. Some of those are more robust than others. You might think of Android as providing very robust communication mechanisms between processes and over the network, whereas Windows and Linux and OS X do not provide as robust mechanisms. And then there are application programs. But most of our view as users of an operating system is defined by the system programs that we use, not the system calls themselves. So if I'm going to edit a file and write it to disk, if I used Notepad because that was provided by my installation of Windows, I might consider that a systems program, and that affects my view of the operating system. Similarly, switching between tasks, the active task, that's part of the operating system typically, and where I Alt-Tab, that is how I interact with my operating system, even though it's not part of the kernel itself, it's just part of those systems programs. So when we design an operating system, there are multiple approaches, and they will vary based on developers' choices, their own personal biases, and what is effective and efficient and supports meeting their goals. So the operating systems are designed typically with, we would like operating systems to be defined by a set of goals and specifications, but they might also be organic, like Windows, MS-DOS, and Linux, and OS X. And they are always affected by their choice of hardware and the type of systems. So we also need to start employing some software design methodology of separating goals. There are different types of goals. There are goals for the users, that those should be convenient, that it's easy to learn, that the system is reliable, which reliable is a vague definition, that it's safe, also a vague definition, and fast. But when you define those for a user, those can be the goals of the user with respect to the operating system. From the perspective of an operating system designer or implementer, it would be nice if it were clearly designed and easy to maintain. It should also be flexible, easy to extend. It should be reliable, meaning that there are few errors, and efficient, where efficient also has a very vague definition. But if you set those as goals, you see that they might compete at times. That efficient computation may not result in fast execution for a user, because efficiently using a resource to, say, calculate the 15 millionth digit of pi, well, then we should dedicate the processor to do that efficiently and never swap out. But if the user would like to, say, browse a web page while calculating all those digits of pi, it wouldn't seem to be a fast operation. And part of these system design choices and being good software engineers is to separate our principles. The difference between policy and mechanism is a very powerful tool and underutilized. The policy says what will be done, and the mechanism is simply how to do it. So if the policy is to restrict Joe from seeing all of Karen's files, the mechanism will support that operation. And separating those two allows them to be flexible. You could imagine that if we were preventing Joe from seeing Karen's files and we hard-coded that into the operating system and compiled it, well, that wouldn't be very flexible, and anytime we needed to change that policy, it would be a challenge. But a flexible mechanism that would allow Fred to specify which files Karen could have access to dynamically after the system is running is much more flexible and allows that policy to be implemented. So the separating those two concepts, those two principles between policy and mechanism allows us to be better software engineers when thinking through our problems. And when we don't have a lot of support for those mechanisms, and if we were to even try to take this concept of file protection in MS-DOS, it actually wasn't possible because we didn't have this idea of dual mode operation, that there was user mode and kernel mode. So an application program had access to every device on the system under MS-DOS because the underlying hardware didn't have that dual mode operation built into the processor itself. So there were the idea of device drivers and resident programs, and the applications could use those, but they could also just subvert them and go straight to those device drivers. Unix, or what is now Linux, has suffered from the same limitations initially because the hardware was not dual mode, but it did divide responsibilities to system programs and the kernel, and this view is the one that's taken more commonly, that everything below the system call interface and above the hardware, the physical hardware, that's the kernel, and file systems and CPU scheduling and memory management are all part of that kernel. So when we take a look at how that structure looks, we can see that it's a little heavy, it's a little fat around the middle, it's got a spare tire. So we have our users with their shells and their command compilers and interpreters and their system libraries sitting above the system call interface. But then within the kernel, we have handling of interrupts, signals, communication, file systems, managing disk and tape drives, scheduling processes, managing memory, managing virtual memory, and then it has to interact with those hardware controllers. So that portion around the middle is heavily weighted. And when it's a monolithic kernel, meaning that you build everything in all at once, that becomes a very heavyweight kernel and not generally applicable. So we would need to be careful when we deploy such a system. A more conceptual idea is that of the layered approach. That at layer 0, this is not to be confused with ring 0 for access levels at the moment, but the operating system is divided into layers, where at layer 0 is the hardware. And only those calls at layer 1 can actually interface directly with the hardware. And then at layer 2, they can only interact with layer 1. So each layer insulates the other from calls being made. And what this gains for us is modularity and ease of maintenance and debugging. So if we test the layer 0 to layer 1 interface and we know that that's good, and there are no bugs there, then when we have a problem at layer 2, we know that it's either in layer 2 or somewhere between the boundary of layer 1 and layer 2. And doing so, if we have these multiple layers, you can see that, well, if layer 2 only invokes layer 1 and that code is correct, I can replace layer 0 and I have new hardware, with new hardware. And to make a new system work correctly, a new operating system work correctly, all I have to do is properly implement layer 1. I don't need to worry about layer 1 all the way up through n. So this allows us to ease migration to new hardware, and that development cost is much lower on that new hardware. So we see how this could be conceptually very attractive for highly disciplined software engineers that want to do the right thing. But there are some real challenges in how do you define the layers, and how do you plan for future features. You may not be clairvoyant. It's very difficult to predict the future and all the layers that you might need. So that can be an issue of planning for those in the future. That also means that you might spend development time developing layers that you anticipate will be used but won't be used for years. There are also maybe conflicts. Does the scheduler and virtual memory live at the same level, at one level above another? Well, the efficiency and need for changing when jobs run so that memory pages are available or virtual memory is being allocated, they may need to have some interaction. So that conflict may exist. You may not be able to have strict layers. There might need to be some fluidity between them, which breaks the nice modularity that we had. And it is certainly less efficient because the mechanisms for passing information between layers is a communication mechanism. And that communication mechanism must be supplied by the operating system, whether that be shared memory or message passing, that will take more time rather than just accessing the same memory space. A microkernel is motivated. It appears to be motivated by the layered approach, that we take as much out of the kernel as we can and we move it into separate applications. And Mach is the only microkernel that I know of. There may be others. Oh, that's not true. Mach is this way. The Integrity operating system is this way as well, where the microkernel contains only the smallest primitives, mostly message passing and scheduling and memory management. That's about it. So the main purpose of the kernel is to facilitate communication between the other elements that live either in user space or our system applications. So in this way, it's very easy to extend a microkernel because you write a wholly separate program. And by doing so, it's of course easier to port, and it's more reliable because there's less code running in the kernel, and it's more secure because, well, the applications that perform operations on devices are moved out into user land where they are the only ones given permission again. So they can be heavily inspected and beat upon for security tests. But again, the detriment here is performance, that swapping between user mode and kernel mode is expensive, and so that will drive down performance. So again, to illustrate, we have the kernel that interfaces directly with hardware, and messages are passed between those user mode processes that handle some of the operations that we might have put in one of our layers or in our single kernel. So again, it's easier to extend a microkernel, easier to port, more secure, but the disadvantages are the performance overhead is high, and then what services should remain in the kernel, because there can be many arguments towards efficiency for saying, okay, this is super inefficient, let's move it into the microkernel. And if you keep making those arguments, well then, you've gone from a microkernel back to a macrokernel. And that leads us to where we are today with most modern operating systems. And that compromise is modules, where our kernels have loadable modules. So a kernel will bring in a module to, say, control your printer or to control your GPU. And those modules are developed independently, they're compiled independently, but then they are loaded at runtime and memory expanded to service them within the kernel. To do so, the kernel has to have an API for those modules to register and unregister and communicate. And this is what we see in Linux, OS X, FreeBSD, and Windows. So as a small tangent, we will talk about virtualization, something that will come up for us and that we want to have a good handle on before we go too much further. And that is a virtual machine. And in the purest sense, we can think of a virtual machine simply as a process that implements another computer. So there are two types of virtual machines. There's a system virtual machine and a process virtual machine. And what this does is encapsulate those resources that the processes running within the virtual machine have access to. So a system virtual machine is something that will run an entire operating system, and the machine that hosts the program that is the virtual machine executor is called the host. So the host provides the virtual machines the resources that they will need, like processing time, memory, file allocation of the actual physical device. Then the guest OS runs within that encapsulated environment using those portions of the device. And so this is something that you might see in a server, where I would have one piece of hardware with 24 processors on it, and I could sell or rent every month one of those processors to a distinct individual, but they would want to be sure that their machine was dedicated, so I would give them a virtual machine to do that. And clearly this has issues of being less efficient because there's that level of indirection for those processes running within the virtual machine that is then given to the host to run them, so that's a little bit slower. And there are stability issues which are unrelated to the guest operating system. If I were to, say, have some financial difficulty and I had guaranteed every single one of those 24 users a whole processor to themselves, but this month I ran out of money, so I started renting 48 processors, and so they were shared between 2 users, well, now my performance goes down. And if demand goes up by those other users, well, then one user may suffer. Additionally, power outages for the host OS will impact all of them. A process virtual machine typically runs an application, and this has been sometimes described as a sandbox where only the application runs within that one sandbox. And so that virtual machine is created when the process starts and destroyed when it exits. And this isn't necessary for, this doesn't service a whole operating system, this serves a particular application. You can think of this in the Java virtual machine, which spins up when you begin your Java program and then shuts down when that Java program ends. Similarly, Docker and Node are examples of process virtual machines. When we fully virtualize, this is a system virtual machine. That's where we're virtualizing all of the hardware. And that means that any virtual machine can run an operating system that can support that simulated hardware. And so this means if you're simulating a processor, you have to provide the whole instruction set, all of the I/O operations, the interrupts, memory control. So VMware and OS, VMware, VirtualBox, and there's one more I can't remember of, are examples of that. And this can be helpful if you're trying to develop an operating system. It's also helpful when designing the hardware itself, so that you can say, oh, I have an operating system, I know that it works. Let's try to implement the virtual machine, run it on one of these virtualized platforms, and see if that matches up. Emulation is something else. Emulation is to duplicate a piece of hardware that you may not have access to. So in one example is the Java virtual machine, which is very strange to think about, that the Java virtual machine doesn't exist in any physical device. It is a specification of an abstract machine. But that abstract machine is the Java virtual machine, and you write bytecode to run upon it. So that is an emulated machine. There is no correlation between one instruction. There is not necessarily a correlation between a Java virtual machine instruction and the instruction on your x86 processor. And if there was a one-to-one correlation, the bytecode for each of those would be different, likely. So some emulator that you might be familiar with is an NES emulator, or an SNES emulator, or a Nintendo 64 emulator. And those used custom processors. So what happens is that on your computer, you will run a process which emulates one of these processors and all of their hardware and memory that's available, and that is how you're able to play your games. So again, system VM, fully virtualized, and they have their own. In the case of VirtualBox, there are specialized video adapters and network adapters that they have then written drivers for the other operating systems that will run as guests upon them. One of the vulnerabilities there, though, is that when the guest OS has the same architecture as the host OS, there may be no translation, so the operating system, the underlying operating system, will have full access to all of your hardware. Again, the Java virtual machine is an emulated machine because there is no actual machine. And the idea is that the JVM is a specification outside of the Java language. And the JVM specifies bytecode that implementers of the JVM may implement in a way that is more efficient than others. And this is particularly true of Dalvik, which runs on Android, that has that it considers the use of memory and processing time more importantly than it does for performance, because mobile devices have such limited resources compared to a desktop. So similarly, so the way that we get this to run is that we take our class files and we build them into we take our class files, compile them. We take our Java files, compile them to class files. Using the class loader, we get that on the Java interpreter, which is an emulated system, and that makes the appropriate system calls when necessary to the host system. And the last thing to mention in virtual machines and multiple operating systems is dual booting or multi-booting versus a virtual machine. So the way that you dual boot a machine is that you shut it down, start it up, and select one operating system or another via your bootloader. For a virtual machine, you start a process, shut it down. When you dual boot, you get the full capability of the hardware available to you. In a virtual machine, you don't have that option, and the host operating system may interfere with your performance of your virtual machine within it. Dual boot, you have to pre-partition your hard drive for each operating system, whereas in a virtual machine, you may grow or shrink that disk when you need it. And dual booting, file access is more restricted, though you may be able to share partitions across operating systems, but typically you don't because you don't want them to mess things up. And within a virtual machine, there are device drivers for network drives to share files between those guests and the operating system itself. Debugging an operating system, debugging a program can be very difficult and complicated. So to debug is to find errors and bugs and fix them, and one of those bugs might be performance. To support debugging, operating systems may generate log files, and that would just be a record of accesses or information that applications, system processes emit during their operation. On a Linux system, you might look at this as var log messages or dmessage. That's one of those places where those logs exist. One of the distinctions we want to draw between an application and the operating system having a failure of processing. So if an application has a seg fault, that will create a core dump, where core is the memory core. And that's captured by the operating system when the process seg faults or whatever the problem was, and it just drops the contents of memory on disk that you can then use in a debugger to analyze the problem. Well, if the program, the operating system, the program that dictates when programs can run crashes, well, how can it then save memory and write it to disk? And how can it write it to disk if it is in control of disk operations, and maybe even the disk driver itself is bad? So this is, it's a sort of a chicken and egg. How do I get this dump out? One of the techniques that an operating system may employ is to reserve a portion of the disk that is not formatted. It doesn't require complex file operations, but it is reserved for those dumps. So the operating system will say, oh, I've crashed. I'm going to take as much of my memory as I can, place it into this special location on the hard drive, and then reboot. When it reboots, that crash dump will be inspected by the operating system and taken off of the special location on disk, moved to a reliable place on disk that the user could inspect to try to handle whatever problem that arose. Similarly, performance tuning is a debugging operation, and there are tools to help us with that. The first is just your task manager or top, and then more invasive tools that are, and I mean invasive in that they can see more into your programs like dtrace, and debugging hooks can be added to your operating system as well. Ideally, operating systems should run on all, we would like the perfect operating system to run on all devices, and as a operating system writer, you will have this as one of your goals, specifying which devices this operating system should run upon. However, every device has a different set of hardware, whether that's a different GPU, an integrated GPU, or an external, a discrete graphics card, how much memory is available, if there is caching, if there's a coprocessor. All of these portions of the target hardware will vary with each device. So then that brings us to the concept of system generation, sysgen. And there are multiple ways to configure a system, configure an operating system to run on hardware. Whether you ask the user to provide detailed information about what hardware is available, or if in the process of installing the operating system, there is a program that queries the available hardware to then install or compile the correct drivers and services for the operating system while it's being installed. The sysgen process, for those of you that compile your own kernels, that's make configure in your Linux source directory. And if you don't use that and you use an autogen kernel, then that's an autogen kernel. And the autogen kernel will try to probe as many devices as it can, come up with the list of modules that it needs, and prepare those for the next boot. And how do we boot? Well, when a system is powered on, which is still vague as well, when you flip that power switch, your motherboard turns on and your CPU may or may not start running. But that motherboard has a piece of firmware that will run, that will set a location for the processor to run, or it may be that your processor has this built into it at build time. It's one of the two. We don't know because it's dependent on each processor itself. There is a typical three-stage process here that this initial boot code runs, and that loads a bootloader, and then the bootloader finds the operating system and loads it. And this is necessary in today's world because there are so many devices with so many hardware interfaces that you can't store all of them in that little bit of initial ROM that the initial boot comes from. So those bootstrap loaders, the one in Windows and on OS X, they actually live on your hard drive because that's how big they are. They can't fit on these small pieces of ROM or EEPROM. And ROM stands for read-only memory. EEPROM stands for programmable read-only memory, so you can program it once or a few times, but not as much as you can program, say, your hard drive. So we look for that boot block in our ROM code that tells us where to get our bootstrap loader, which tells us where to get the rest of the operating system, and minimally what drivers we need to get going. So the one that you might be most familiar with is Grub's bootloader. There's also one for Windows that if you've ever looked at your UEFI portion, boot partition, that lives in there as well. So Grub will then find the kernel, minimally prepare the disks, and get that kernel running. And now once the kernel is running, then that begins loading the rest of the system resources. So our objectives for today were to describe our operating systems, system calls, and some of the motivations that we have for designing operating systems and how they may fall out. We went over loosely how operating systems are installed and customized and how they boot. So I will look forward to your questions in the discussion section. Please make sure you post them there, and I will see you in the next video. Thank you so much.